factoring polynomials. Let's review what defines a polynomial. A polynomial has three components in the equation, such as this one right here, y equals 2x squared plus 3x minus 13. We designate each part of these components with a letter to represent it. It's actually the number in front of it we're representing. The a goes in front of the squared component, in this case the 2x squared, and a equals 2 in this case. The b goes in front of the single variable, in this case 3x, so b equals 3. And then c is the constant, in this case is minus 13. In general, we classify a polynomial in this form as ax squared plus bx plus c. And these letters representing the numbers will help us determine how the polynomial works and how to factor it. When we graph an equation of a polynomial, it has a U shape. And the U shape is shaped upward if that x squared is positive. If the x squared is negative, it's shaped downward. There are several labels here I want to discuss. And again, this is the equation we were just looking at. This is the actual graphical component of y equals 2x squared plus 2x minus 13. The vertex. This is the highest or lowest point on a quadratic function, depending if it's opening upward or opening downward. The y-intercept. This is where the equation crosses the y-axis, as we show here, and where the x equals 0. The x-intercept, where the equation crosses the y-axis, x-axis, and the y equals 0. If you notice here, we can have two x-intercepts. We could have one, we could have none. Why are these terms important? And more importantly, is it important in the real world? And I want to show you why it is. Epidemiologists who study the spread of diseases often model the sickness rates and death rates of these diseases to determine both the rate of death as well as the rate of the sickness. We can use this information to determine how severe the disease is going to be, when it's growing, when it's declining, the spread of the disease and the speed of the spread, and then plan for how many hospitals, hospital beds, medical materials, doctors, nurses, and other support mechanisms are going to be needed to counter this epidemic and probably try to reduce it, in fact. And this is why we look at this. We just went through a pandemic with COVID-19, and again, a pandemic is a global epidemic. But when we look at in history, we know why epidemiology is so important. Now, 6.9 million people died from COVID throughout the world as of May 2023. Well, let's compare this to some other pandemics we've had throughout history. Smallpox, which we have eradicated in the last 40 years, killed 300 million people or more. Measles has killed 200 million people. The Black Death, bubonic plague, killed 75 million people. And very concerningly, only in the last 100 years we had the Spanish flu, which killed anywhere from 50 to 100 million people in only 2 years. And these were young, healthy people. Not only was the Spanish flu devastating, it pretty much was the whole reason World War I ended. Both sides were so sick. And death toll was 50 million at least. There were so many people unaccounted for, that's why it might be as high as 100 million. And you see some of these areas here they're talking about on these pictures how many sick soldiers there were, telling people not even to spit because of influenza. In fact, the Spanish flu killed more people in 1918 than weapons did on both sides. The origin of the Spanish flu is not actually Spain, which is a neutral country, but actually Camp Funston in Fort Riley, Kansas. And it has an avian origin, in other words, it was a chicken. And the signs and symptoms were fever, nausea, aches, and diarrhea, flu. But it really hurt young, healthy people, so through a cytokine storm. And you see how quickly it spread in 2 years throughout the world. But the Spanish flu was the first time in history that we could gatherize global data that could be collected and analyzed. Here's the death rates in the Spanish flu month by month from January 1917 through December 1919. There were 3 peaks here. And if you look at this, these are quadratic functions. There are parabolas here, and they're pretty close. And if we know this, we can actually establish timelines of how severe it's going to be, because we can determine what the equation is. If we know the y-intercepts, we know when it's going to start, when it's going to end, and how severe it's going to be. When it's going to start, when it's going to end, and how severe it's going to be. We can also use the vertex to see what the high point of the disease will be, and when it's going to start descending. We also know if we can alleviate at any certain point how many lives we can save. And this is why we need to learn polynomials and quadratic functions. We can factor the ax squared plus bx plus c into the simplest components. This is how we're going to find the x component for the x-intercept, the y component, and the vertex, which is so important in determining these disease rates. Let's talk about FOIL first. FOIL is basically how we calculate when we got 2 separate binomials here. It is x plus p and x plus q. We do the first, x times x, that gives us our x squared. The first on each of these areas. Let me erase this here. And then we do the outside. Outside of this one, outside of this one. This gives our x times q, or qx. The inside for each component, the x times p, or px, or pq, excuse me, px. And then the p times q, which is the last. And that's where the word FOIL comes from, p times q here. And when we put this together, we get that standard form of ax squared plus bx plus c. Here's the x squared. These 2 parts are the bx here, and then this is the c right here. And because if we can find the p and the q, we can find out our x-intercepts. Now, before we go any farther, we should know that that a in front of the x squared, y squared, t squared, the squared component can only be a 1. It can't be 2x squared, 5x squared, 3t squared. The p and the q and the px, qx add up to the b. And that's what makes this interesting. The p and q multiplied give me the c. So we can find our p and our q, and I'm going to show you how to do that. We have our b and our c. And since we know our b and our c, we just got to find p and q. All right, let's take a look at this. Example using the PQ method. I've got a simple equation, y equals x squared plus 9x plus 8. And I can use the BQ method because I don't have any number except 1 in front of that x squared. As you can see right here, this is the equivalent of 1x squared. So, if I can find my p and q, I can find my y-intercepts, where it crosses, and where it starts, where it ends. So, I've got p plus q, as I recalled before, it will equal b. So whatever my p plus q is will equal 9. And then my p times q will equal 8, which is my c here. So I got to figure out what p times q gives me 8 and p plus q gives me 9. I start with my p times q. I'm going to put in all the factors that give me 8 and multiply them together. 1 times 8 is 8. 2 times 4 is 8. Negative 1 times negative 8 is 8. And negative 2 times negative 4 equals 8. Now, these are all factors of 8, and that is where that C comes in. What I want to do next, and I'm going to erase all this here so it's easier to read, I want to determine, I can see my P plus Q. Now, which is it? What I'm going to do is I'm going to take my 1 from here and my 8, and I add them together. 1 plus 8 is 9, and actually that matches that. 2 plus 4 equals 6. Negative 1 plus negative 8 equals negative 9. And negative 2 times negative plus negative 4 is negative 6. So my only one that adds up to 8, multiplies to 8 and adds up to 9 is this one. And that is my 9 here, my 9x. This is my B equivalent. And then my P times Q is my 8 here, right here. So the only one that can be is the one I've circled here. And that would be 1 and 8. So what I'm going to do next is I'm saying it looks like it will be y equals x plus 1 and x plus 8, because that's that 1 and that 8. That's my P and Q. So my P could be 1, and my Q is going to be 8. How do we prove this? I need to see whatever y equals 0. One of these x's has to become 0. If I put in negative 8 for right here, put negative 8 here, negative 8 here, and that's going to give me negative 8 plus 1, which is negative 7. Negative 8 plus 8 is 0. Well, that equals 0 for y. And negative 7 times 0 is 0. So here it is. Negative 8 and 0 is one of the x-intercepts right here. And that is where we were graphing before. The other one, how do I turn it into 0 for y to be 0? And this is, remember, y is 0 all along this line here on the x-axis. So when I'm looking at this, I want to do the same thing with how do I turn it back into 0. And I'm going to look at, now put in negative 1, because if I put in negative 1 here, plus 1, which I've done right here, negative 1 plus 1 is 0, right there. Negative 1 plus 8 is 7, and then 0 times 7 is 0. So it shows if y is 0, then x would be negative 1, 0, and that's where my other point is right here. So this is the solution. X equals negative 8, x equals 8, x equals 1, because they cross for y equals 0 at negative 8 and negative 1. Now we're going to find the vertex. The vertex, as I said, the high point or low point, depending on which direction it is going. I got my A, my B, and my C. And my vertex is very simple to find. It's negative B over 2A. A is 1. My B is 9. And to find the x component for my vertex is I simply put in what my B is, what my A is into this equation. And my B is 9. My 2 is when I multiply by my A. So it's when I put this together, it's negative 9 halves, or negative 4 1/2. And that seems to coincide right with here. Here's 2, 4, 6, and here's 5. And it looks like it is at 4 1/2. So that part is correct. My x coordinate is going to be negative 9 halves, or negative 4 1/2. Now what I'm going to do is I'm going to plug in that negative 9 halves back into the original equation. And that takes some time here, and I've shown you how to do it step by step. But what we're looking at here is I'm going to plug in 9 halves to x squared plus 9x plus 8, which what I've done here, and it's a lot of little fractions because that original thing's a function. But by the time I get to the answer, I get the answer for the y coordinate, because I put in negative 9 halves for x, is negative 12 1/4. which looks like that's what it's about here. Here's 10. These go by twos. Here is 12 right here. It's a little bit over 12. 12 and 1/4. So this looks like it's absolutely correct as well. So my coordinate for the vertex is being -9/2, -12.5. Where do I use this? I've just showed a cool way to find out simply where the vertex is, why the x coordinates, x intercepts are, the y intercepts are for epidemics, as we've shown. But there's other areas: disease growth and decline, healthcare. We do it in business operations to determine market growth. Or we have all the way from early adopters here. And you can see this is a parabola basically. The late adopters to a majority of people purchase something and is over time. It is actually a quadratic function, a parabola, when we have radars, so we can focus on areas. Even our nation's defense uses parabolas for ballistic missiles. Chemical and molecular structures to determine points of heat, points of cooling, have basic parabola structures, and even biochemical structures of our molecules also have that, as you can see right here. A lot of places we use parabolas and need to find out the vertex, the x-intercepts and the y-intercepts, because we can do a lot with that.